In this screencast, we're going to introduce a new property about angular velocity that I hope you'll find very intuitive. And it's this idea that we can take the angular velocity of reference frames and add them up just like a vector sum. And that's going to help us work our problems. It's also going to help us be more practical when we make measurements in the real world. So let's take this example of this real physical system. This was the robot arm that we saw way back in Chapter 2. And we decompose this into a series of links, but let's add one more piece to this arm. Let's say that we've got a telescoping hand here as well. So that gives us a link from O to O prime. That'd be this first joint, or this first link in these two joints. And then we've got a link from O prime to O double prime there, and then a link from O double prime out to point P. But we're going to say that P can also telescope. It can extend. So essentially, we can have a velocity of P, and we can observe that in the C body frame. And so as soon as you start seeing observations made in these body frames, or this motion is relative to O double prime, we should start thinking about the transport equation. And let's use the transport equation to find the velocity of point P with respect to O as observed in the inertial reference frame. So we define the position vector of P with respect to O as the position vector of O double prime with respect to O plus the position vector of P with respect to O double prime. To find the velocity of point P as observed in the inertial reference frame, we'll differentiate each of these components in the vector sum individually. So the time derivative of the position vector O double prime with respect to O as observed in the inertial reference frame is the velocity of O double prime with respect to O as observed in the inertial reference frame. So let's say that we know that quantity, and then when we take the time derivative of P with respect to O double prime in the inertial reference frame, this is where a transport equation comes in. And so we've defined that, or we're observing that in the C frame, so we'll take the time derivative in C of that position vector, P with respect to O double prime, and then we need to add the angular velocity of reference frame C as observed in I, and cross that with the position vector of P with respect to O double prime. And so these second two terms are a direct application of the transport equation. So let's think practically here. The reason why we use this transport equation for these two terms is because we've just said that we're observing the velocity of P as observed, or with respect to O double prime, in the C frame. Now think for a moment how we would actually make that observation in reality if we had this robot arm. We would put a sensor on this reference frame C so that we could observe that hand moving in and out, telescoping in and out. And the way that we do that is with what's called an Lvdt. It's a linear variable differential transformer, which would then give you a voltage potential that corresponds to the position. You could take the time derivative of that, and now you've observed both that position and that velocity within that C frame. And remember, this C frame is rotating, and that's how we've expressed this. It's an omega C with respect to I, or it can rotate. So that means that the C frame isn't necessarily inertial, and most of the time it's not going to be an inertial frame. Therefore we use the transport equation. However, we just tossed this term in here, this angular velocity of C as observed in the inertial reference frame. And so far as we've worked all of our problems, we've just assumed that we actually know this. But how do we measure it? Once again, we have to consider the technology that we have and how we make these measurements. And in this case, we're going to measure it using sensors. And so what we typically do here is we're going to put an RVDT, a rotational variable differential transformer, at this joint O prime. And with this type of sensor, we're going to get voltage information, a voltage potential that corresponds not to the linear stroke distance, but instead it's going to correspond to the rotational angle. And so the angle is going to be with respect to, if we put it at this joint O double prime, it'll be with respect to the B frame. So what we're characterizing here with this type of sensor is going to be the angle, and then we can take a time differentiation to get the angular speed, but the angle of the C frame with respect to the B frame. Now this is a really important point because what we've just described is that if we get this angular velocity that would come from an Lvdt, we're actually measuring omega of C as observed in B, because they're connecting these two reference frames C and reference frame B. But for our transport equation, we need to have omega of C as observed in the inertial reference frame, which is 2 reference frames away. So similar to how we put the Lvdt at O double prime to make an observation of the angular velocity of C as observed in B, we can do the same thing at the joint O prime and observe the angular velocity of B in A, and then put an Lvdt at O and make an observation of the angular velocity of A in I. Notice here that these are all vectors. We have an angular velocity vector with 3 angular velocity vectors, and so because they're vectors, they all add just like vectors. They're geometric quantities. And so with these observations, we can simply add up the angular velocities, C with respect to B, or C as observed in B, B as observed in A as observed in I, add them up, and we can get the angular velocity of C as observed in I. And with this formulation, we've now skipped the step of directly linking C with I, but we've put in intermediate steps in which we link the individual reference frames with each other. And so this allows us now to parameterize our problem, or to use our coordinates in a different way. We can now express the angles that relate these reference frames directly to each other. So let's say if we put a theta 1, that's the angle between I and A, we can now make an angle between A and B that we can call theta 2, and then an angle between frame B and frame C, theta 3. And so notice this is different from what we've done before because we've always linked our reference frames directly to our inertial reference frame. And here we're now linking the orientation of our reference frames back to the previous reference frame. Now I need to add a strong note of caution here. We came to this conclusion about adding our angular velocities by working through the transport equation and knowing what we know about how these velocities relate to each other. And there's an elegant derivation of this in the book that I encourage you to look at, which comes to the same conclusion in a purely analytical style. But the point here is that we came up with these angular velocities and said we can add those together. And don't be tempted, and here's where you can really make a big mistake, don't be tempted to say, well, you know what, the angle of link 3 relative to my inertial reference frame, and I'll just call this big theta, and that there's a such thing as the big theta vector, let's say in the E3 direction, in which we just add up theta 1 in the E3 plus theta 2, which happens to be in the E3, plus theta 3, which happens to also be in the E3 direction. There's no such thing as angular vectors. And so don't be deceived in this idea that we've got this angular position vector that we can then differentiate into an angular velocity vector. It looks this way in planar motion, but as soon as you move out of planar motion, that doesn't hold at all, because we have something called a non-holonomic constraint. And that's a fancy word that just means that you can't differentiate between an angle and then an angular velocity, or you can't integrate from an angular velocity and then get an angle. There are definitely ways around this, but it's beyond the scope of this course. So just keep that in mind in how we got to this conclusion. We went directly to the velocities, we ended up adding up our angular velocities, and we'll be able to use this repeatedly in problems as we work in the future in relating reference frames to each other.